Hello everyone, today I'll be presenting our work on relating confidence judgments to temporal biases in perceptual decision making. Humans make decisions by integrating information over time. Researchers often study the mechanisms of decision making via evidence integration tasks. Let me give you an example. Suppose a participant sees a series of stimuli presented one after another, denoted by E1, E2, and so on. Now you can think of each E as momentary evidence that needs to be integrated for decision making. Here, each stimulus or evidence is a texture which is either oriented plus 45 degrees or minus 45 degrees. At the end of presentation, the participant has to choose which orientation was the majority. Now, we can compute how much weight was given to each piece of evidence over time in decision making. Interestingly, it has been shown in previous studies that sometimes subjects weigh early evidence more, also called the primacy effect. Sometimes they weigh each piece of evidence equally or optimally, and sometimes they weigh later evidence more, also called the recency effect. We resolved these discrepancies observed in temporal weighting in previous studies, and let me walk you through the main concepts of that work that also form the basis of our current contribution. Let us first consider what an ideal observer would do in such a task. An ideal observer would essentially use the information in the evidence to infer the correct choice for the trial denoted by C, or compute probability of C given E. Now, in our previous work, we first acknowledged that the brain does not use sensory observations, say for example activity on the retina, to directly make the choices, but instead the brain bases decisions on intermediate sensory features in the visual cortex, here denoted by X. This implies a partition on the information each stimulus holds about the correct choice. We denote one part as the sensory information, which represents the amount of information between stimulus and the intermediate feature, and the other as the category information, which represents the information between feature and the correct choice. Sensory and category information together combine to give total information available in the stimulus. Now, for sequential tasks consisting of multiple frames of evidence, category information typically corresponds to the proportion of frames which are consistent with the correct choice. Hence, high category information means majority of frames will have the same orientation, as shown to be plus 45 degrees here. But low category information means that the orientations go back and forth across frames. Sensory information, on the other hand, corresponds to how noisy each piece of evidence is. Hence, high sensory information would mean that each piece of evidence clearly indicates their orientation, whereas low sensory information means that it is very hard to read out the orientation from each piece of evidence, as shown here. Okay, now you can imagine that it is possible to come up with different combinations of the amount of sensory and category information in a task. Now let us look at the space of all possible combinations of sensory and category information. When both are high, that is, each evidence is clearly visible and all of them have the same orientation, a subject is at perfect performance. Now, keeping category information fixed, if we move along the x-axis towards 0, it reduces sensory information, as shown here. Similarly, keeping sensory information fixed, if we move along the y-axis, then category information is reduced and the evidence and the orientations of the evidence go back and forth, as shown here. Now, if both of them are low, then each evidence is hard to see and they vary a lot in their orientation, and we are expected to be a chance performance in that case. Therefore, going from perfect to chance performance, we'll have a region in this space where subjects will have 70% chance of being correct, which we also call the threshold performance, denoted here by the black dashed line. Note that along this line, we can construct tasks which are equivalent in difficulty but differ in their relative amounts of sensory and category information. Now, another aspect in our previous work is that in our model, the sensory neurons denoted by X represent posteriors. Now, one can think of it as our current belief about the correct choice of the trial influences our sensory percept of the upcoming evidence. So here, X2 not only reacts to information from E2, but is also influenced by prior expectations about the correct choice so far. That is P of C given E1. And this continues. We denote this by an arrow coming from C to X. Now, going back to our task space, for a task with low sensory and high category information, each piece of evidence is very noisy, but they all have the same orientation. Now, this can be viewed as weak likelihood due to noisy evidence, but strong prior due to the knowledge that each piece of evidence is highly predictive of the correct choice. Such a feedback loop between X and C results in double counting, or seeing what you expect to see. That is, if you somehow perceive that the first orientation is plus 45 degrees, then you keep perceiving that orientation in the following frames because they're extremely noisy. In our previous work, We show that by performing approximate inference in such a model, we obtain primacy bias due to double counting under this task. Now, for the case where the sensory information is high, but category information is low, that is, evidence is clearly visible, but the orientations change rapidly across frames, we have strong likelihood because of the clear stimulus, but the strength of feedback is weak since orientation of any one piece of evidence is not highly predictive of the correct choice. We have very less information about the correct choice from each piece of evidence. So, in our previous work, we show that approximate inference for such a task gives optimal or recency bias. Now, so far, I built the intuition of our previous work, which successfully explained prevalent types of temporal biases via approximate inference in a hierarchical model for the space of tasks defined by the sensory information and category information. Now, the question that we ask next is whether sensory information and category information also affect our confidence judgments. Now, in evidence integration tasks, the probability of the correct choice is computed using the sequential probability ratio test. And for this, with every piece of evidence, we compute the log posterior odds of the two possible choices, and it can be shown that the log odds for frame F is the sum of log odds up until frame F-1 and the estimate of log likelihood ratio implied by the current piece of evidence. Now we can compute the evolution of the log posterior odds over time for evidence integration tasks across various models and for different experimental conditions. So we show the approximate inference model on the left, ideal observer on the right, and the low sensory high category condition on the top row and the high sensory low category condition in the bottom row. Now the evolution of the log posterior odds over time across trials is shown here by thin red lines for the LSHC condition. And each line is one trial, and the distribution at the end shows the distribution over the final log posterior odds. Note that the strong feedback between the decision and the sensory area results in the log posterior odds being pushed further and further away from zero, denoted by the black line. Intuitively, this happens because your belief about one particular choice becomes stronger and stronger over time since you keep seeing what you expect to see and reinforcing your belief even when the actual evidence is entirely ambiguous. But for the HSLC condition, due to weak or no feedback signals, the actual posterior odds stay close to the true posterior based on the external evidence. That is, they stay close to the zero line shown in black. Now, for an ideal observer, there is no difference in the two conditions as expected. And note that the ideal observer qualitatively matches the approximate inference model for the HSLC condition shown in blue in the bottom left. Now, since the belief accumulated about the choice of the trial is denoted by the log posterior odds, we use that as a proxy for confidence of a subject in a trial. Here, in the y-axis, we plot the mean of absolute log posterior odds as confidence. Now, as expected from the evolution of the log posterior odds, the mean is higher for the red LSHC condition than the blue HSLC condition in our approximate inference model, whereas they are comparable in the ideal observer model, or actually equal. Now, going back to our task space, the difference between the mean log posterior odds across the mean log posterior odds across the approximate and the ideal observer predicts that our model is overconfident for the LSHC condition due to strong feedback between decision and sensory areas, and almost no difference between the blue bars predict optimal or underconfidence in the HSLC condition. Now, if we simulate the approximate inference model for all possible points in the task space, we see that for threshold performance shown by the white curved line, the mean of absolute log posterior odds for the LSHC condition shown by a red dot is higher than that for the HSLC condition shown with a blue dot. Now, that means that our model predicts higher confidence or overconfident confidence reports for the LSHC condition than for the HSLC condition. Okay, now note that if we do the same for the ideal observer model, the red and the blue dots have comparable values, meaning that the ideal observer model would not predict any difference in confidence reports across the two task conditions. Okay, now connecting our current prediction to our previous work, what our model predicts is that for the LSHC condition shown in red, we should not only observe primacy but high confidence reports, and for the HSLC condition, we should not only expect an optimal or recency bias but low confidence reports. Okay. Now, to test our model predictions, we collect new data in a dual report task with explicit confidence reports for both the task conditions. Now, each trial starts by presenting a black circle around a white cross in the center of a gray screen, indicating the location where the stimuli will appear, and then 10 stimulus frames are presented around the cross, each lasting for 83 milliseconds. After the 10th frame, a noise mask with no orientation energy is presented to prevent any after images. Following that, participants make a decision by pressing a button indicating whether the majority of stimulus frames were oriented plus or minus 45 degrees. And then they also report their confidence by pressing 1, 2, or 3, 1 being the least and 3 being most. Finally, an auditory feedback is played at the end of each trial. Now, as you can see, under threshold condition, for the LSHC condition, each stimulus is very noisy, but almost all frames have the same orientation. The task is similar for the HSLC condition, except here in the threshold regime, each stimulus, though clearly visible, the orientation across the frames go back and forth, making the task hard. Okay, now in the LSHC condition following Lang et al., we run a 2:1 staircase on the amount of orientation energy in each frame of stimulus, while 9 out of 10 frames had the same orientation on average across trials. And for the HSLC condition, we run a 2:1 staircase on ratio of frames with same orientation, while keeping the orientation energy per frame very high so that participants could clearly see the stimuli. Okay, now 10 naive participants performed both the task conditions, and first we confirmed that the participants were able to perform both the tasks by plotting their performance on the y-axis, and for the LSHC condition, the x-axis denotes energy in favor of plus 45 degrees in each stimulus frame, and for the HSLC condition, the x-axis denotes the fraction of stimuli in favor of plus 45 degrees in a trial. Now, as you can see, these psychometric curves confirm that the observers could perform the task equally well in both conditions. Now, we next confirmed the validity of the participants' reported confidence for both the conditions, and we plotted on the x-axis for both conditions the confidence reports, and in the y-axis their accuracies. And as you can see, higher the accuracy, greater is the confidence, showing that the reported confidence on average tracked the subject's accuracy. Okay, finally we computed the temporal weights using logistic regression, and we do indeed see a primacy effect in the LSHC condition and an optimal weighting in the HSLC condition. We also fit exponential curves to these weights to obtain an estimate of slopes, and as you can see, the slopes increase going from the LSHC to the HSLC condition. Now, I want to emphasize that both these plots replicate the findings of our earlier study with new observations, with new observers or participants performing this task, and this demonstrates the robustness of the effect. Okay, finally, we compared the participants' confidence reports between the two conditions using trials at or below threshold performance. So in the x-axis, we plot the mean confidence reports for the LSHC trials, and in the y-axis for the HSLC trials. So each dot basically corresponds to one subject, and the green dot shows the population mean. Okay, what we find is 8 out of 10 subjects have significantly higher confidence in the LSHC rather than as compared to the HSLC condition. With two subjects, the other way around, but not significantly so. This agrees with the connection between the nature of bias and the confidence judgments predicted by our model. That is, high confidence judgments co-occur with primacy when sensory information is low and category information is high. Interestingly, the two participants who showed similar confidence in each trial condition also showed small or negative effects with respect to changes in the temporal weighting slopes, as shown with dashed lines in the figure in the center of the screen. Okay, to conclude, we built on our previous work and found that approximate hierarchical inference induces biases in explicit confidence judgments. These biases in confidence judgments are related to temporal weighting biases in predictable ways. Then we did model simulations and had new experimental evidence to show that overconfidence co-occurs with primacy effect when sensory information is low and category information is high. This work also suggests that approximate hierarchical inference may provide a computational basis for the emergence of biases beyond low-level perceptual decision-making. And finally, the model explains how biases in confidence can emerge due to a positive feedback loop between decision-making area and sensory representations. With that, I thank you all for your attention, and here are the acknowledgements.